Hello. Shajan sir. Shajan sir.
Sir.
Audible thane?
Hello sir. Audible.
Is it audible? Okay.
Yeah, it is audible.
Okay.
Yeah.
Good evening. I welcome everyone to the webinar on research challenges in surface engineering. I would like to thank our college chairman, directors, principal for providing us an opportunity to conduct the webinar. We are happy to welcome you all for this wonderful occasion. We are happy to welcome our resource person, Dr. Sathish, Associate Professor and Head of the Department, Mechanical Engineering, Aalim Muhammed College of Engineering, Chennai, who was an expert in surface engineering. He has over 15 years of experience in this field and has published more than 15 research papers in various international journals. He has also worked on various projects funded by CSIR and DSP. I am glad to welcome you, sir. I also welcome all the participants who have shown interest to participate in this webinar. I would like to hand over the session to Dr. Sathish.
So thank you very much for your introduction, sir. So very good evening, one and all. So directly I will share my PPT. Is it visible, sir? Hello, sir?
It is visible,
Excuse
sir.
me, sir.
Okay. It is visible, sir.
Okay. Very good evening, everybody. So my presentation is regarding the topic research challenges in surface engineering. So this is the outline of my talk. So first I will be discussing about the need for surface engineering, and I will also discuss about the various types of surface coatings available, and I will introduce thermal spray coatings, and followed by that I will be discussing something about the importance of thermal barrier coating, and I will also give brief introduction to biomaterials, and subsequently I will discuss something about nanoceramic coatings for biomedical applications. So as we all know that majority of the components failure exactly originates at its surface due to the mechanisms involving wear, corrosion and fatigue. So in order to overcome these issues, surface engineering is highly essential. So another important thing is it is a much cost-effective method to meet both bulk and surface property needs of virtually all imagined application. So if you look at the surface engineering is a highly interdisciplinary area. So it involves mechanical engineering, material scientists, physics, chemistry, and all the people are involved in this particular surface engineering. So for instance, so if you assume that if you are having two materials which are making contact with each other, and if there is a relative motion between these two materials, so what will happen is you will end up with friction, and finally it will lead to wear. So if you want to reduce the wear, so one method is you can apply some lubricant. So that lubrication engineers or chemistry persons. So on the other hand, another method for reducing the wear is you can go for selecting appropriate materials. So that part will be taken care by material scientists. So another most important thing is these mechanical engineering people, they will study the contact mechanics existing between the contacting surfaces. Thereby you can minimize the wear to the maximum extent. So apart from that, the physics persons will be actively involved in developing a material or developing an equipment for modifying the surface. So what I want to convey you is So here, surface engineering is not a single area. Anybody can do research on surface engineering. And coming to the different types of surface modification techniques. So these are the three methods. So one is you can modify the surface by changing the surface chemistry of the material. So for example, if we go for carburizing, so in the case of carburizing, especially on steel, so we will actively diffuse carbon atom inside your steel. So once the carbon is introduced, what will happen is it will occupy the interstitial sites of your iron atom. So thereby your material gets hardened. So what I want to say is, so you are modifying the surface, at the same time you are modifying the entire surface chemistry of that particular product. So that is the first case. So second thing is you can also modify the surface by changing its surface metallurgy. So the best example is if you take the material and if you are applying some heat source and if you are melting over the surface, so what will happen is your material will be brought to the austenitic region. So after that, due to rapid cooling, your austenite will be transformed to martensite, wherein due to the metallurgical changes, your material gets strengthened. So this is about the second category of surface modification. So if we go for the third criteria, we are adding changing things. So basically, these are the three methods by which you are going for modifying the surface. So if you want to enhance the durability of any component, so among all those techniques, whatever I have discussed, coating is considered to be the best option. So if you want to go for coating, so before going for applying any coating, the particular person should keep the following things in mind. So first thing is you have to check your coating is whether it is durable or not. If you go for any application, the first thing is you should notice whether your coating is long lasting. So that is the about durability. And another most important property is adhesion. So normally, so you cannot directly coat any material over any base material. So the most important thing for enhanced adhesion is that the thermal expansion of the base material as well as the coating material should be more or less similar. So if there is a mismatch, what will happen is one material will tend to expand, on the other hand, other will tend to contract. Thereby your coating will undergo delamination. So what I want to convey here is you should choose a material in such a way that so that particular material should have similar thermal expansion as that of the coating, as that of the base metal. So that is point number 2. And again, your substrate should be friendly. So that is nothing but just now I told about thermal expansion. So that is applicable for this. And another important thing is if you are adopting some coating, so that coating should perform well at elevated temperature. So for instance, if you go for steam turbine blade, so when the hot steam is allowed to impinge over the surface of the turbine blade, so what will happen is it will tend to undergo deterioration. So in order to prevent that, you need to go for a very hard ceramic coating. And moreover, you should also see that whether your material is compatible to the environment. So the best example I could quote is in the case of biomedical application, I think you would have heard about hip joint processes and knee joint processes. So in that case, what will happen is there will be a friction between the femoral head as well as acetabular cup. So there a lot of wear and tear will happen. So in that case, we need to go for some wear resistant coating. So if you want to select coating material for biomedical application, you should see that the material which is being incorporated will not create any side effect to the human being. So that is known as compatibility, that we are calling as a biocompatible if you go for biomedical application. So another important thing is the thickness of the coating. So in general, people will think that if you are increasing the thickness of the coating to the maximum extent, you can end up with a very good property. That is not the case always. You should always keep in mind that whenever the coating thickness is exceeding a certain limit, so what will happen is, so it will induce a lot of residual tensile stress. So as a result of that, your coating will tend to peel off. So on the other hand, if you are trying to reduce the thickness of the coating below a certain level, again the wear resistance and corrosion resistance will be poor. So a lot of work has to be carried out for optimization of thickness. So thereby you can end up with a very good improvement in the wear and corrosion resistance. And nowadays you all know that corrosion is a serious challenge in day-to-day life. You can see that a pipe is being corroded due to the impingement of liquid particle over the metal. And if you want to prevent this corrosion, you have to apply some sort of paint so that you can prevent that. And another report says that in United States, there has been a $300 billion of money wasted due to the corrosion. So corrosion is that much considered as a serious issue. And you can see here a steel is being undergoing corrosion due to the formation of rust. So you can use some thermal spraying technique, thereby you can enhance the rust formation. You can prevent the rust formation. And apart from this, you can apply coatings in several industries. So if you consider the first thing, you can see a power sector. So especially if you go for a nuclear power plant. So in nuclear power plant, your materials will be subjected to corrosion in hydrochloric acid, then HNO3, H2SO4, etc. So if you want to protect those materials from corrosion, then you have to go for hard ceramic coating. So in that case, people will prefer alumina coating. It is having very good resistance to corrosion. So in nuclear sector, you can very well go for coating. And if you go for biomaterial, that is in the biomedical field, so as I told you that there are hip and knee joints. So if you consider the hip joint, there will be two regions. So I will be discussing this in detail in the forthcoming slides. So in that femoral head and femoral, that is acetabular calf, so there will be a friction and more amount of wear and tear will take place. So in that instant, you have to go for wear resistant coating. So another thing is, if you are implanting any material inside a human body, so what will happen is the material tend to react with the body fluid, so thereby it will lead to corrosion. So there you have to go for some sort of corrosion resistant coating as well. Apart from that, you can also do some coatings on certain regions which involves wear. So you can see here this laser hardening is being performed over the worn surface, and that we are calling as refurbishment. And another important application of coating in industry is in the cutting tool. So if you go for machining operation, so you all know that whenever you are undergoing machining operation, your tool will be subjected to more amount of wear. So if you want to enhance the wear resistance, you can go for some sort of thin and hard coating. So here you can see a drill bit is being coated with gold colored coating. So this is nothing but titanium nitride coating, and this is deposited by means of a physical vapor deposition technique. So here a lot of people have done so many research work regarding this titanium nitride, chromium nitride, and aluminum chromium nitride, and only few research works have been focused with regard to bilayered or multi-layered coating. That is, layer by layer coating has not been done extensively. So people who want to do research on cutting tool, they can plan for doing multi-layer coating, and they can study the effect of this coating over the performance of the cutting tool. So that is one research people can go for. And another thing is, you can see a mild steel is subjected to corrosion. So there you can apply some sort of thermal spraying technique, and you can enhance the corrosion resistance to the maximum extent. So another important application is in the automobile field. So you all know that in the case of internal combustion engine, only 33% of the heat energy is being effectively converted to work, and some amount of heat loss may occur especially over the piston crown. So in order to retain that heat, so we need to go for a hard ceramic coating over the piston crown, and that is referred as a thermal barrier coating. So I will discuss in detail regarding the thermal barrier coating in the forthcoming slides. And coming to the different types of surface coatings techniques, you can see the first one is electro deposition process, and another one is a PVD, that is physical vapor deposition, and you are having diffusion coatings and surface hardening, then thermal spraying. This is the most important technique, thermal spraying, then followed by that laser cladding. So if you look at the electro deposition process, so you'll be having an electrolytic bath. So you can see electrolytic bath. So inside that you will be having two electrodes. So one is the cathode, which is connected to the negative terminal of the power supply, and another one is the anode. So this is connected to the positive terminal of the power supply. And these two electrodes are immersed in an electrolytic solution. So now the principle is, you are going to establish a potential difference between these two electrodes. So thereby what will happen is, the anode material will move towards the cathode, and thereby you will be getting a very good coating. And even though the process seems to be simple, the most important parameter which will affect the quality of this electro deposition is electrolyte preparation. For preparing electrolyte, we should choose appropriate solvent, and moreover you need to prefer what kind of coating is to be given, that we are calling as a solid solution, that is a solid loading. And together with that, you have to check the pH value, then you have to check the viscosity, then we have to add some dispersant, etc. So stabilization of this electrolyte, that itself is a tedious task. So that is the most important parameter which will affect the quality of the coating. And in addition to this electrolyte preparation, you can also see the power input, how much power is to be supplied for coating. So that is also another important parameter. And in addition to that, the distance between the two electrodes, so that is referred as standoff distance. So these all parameters will have a crucial role in determining the quality of the coating. And if we go for this electrode deposition process, the major drawback for this coating is you cannot expect a uniform deposition. So that is the major drawback. And moreover, this kind of coating is applicable only for conducting materials. So if you look the application, this kind of coating is well suited for enhancing the wear resistance of the cutting tool, and you can also use this coating for decorative purposes. Another most important coating technique is physical vapor deposition, that is known as PVD. Previously I was telling about cutting tool. Generally in cutting tool, we will coat some material using PVD. So you will have a big chamber that is filled with vacuum, and inside the vacuum chamber you will be having a heater. Above that you will be having a provision for holding the target material, or I can say this is a coating material. And above a certain distance from the target material, you will be having a substrate holder for holding the substrate. Here the principle is very simple. You are going to heat the target material will evaporate, and finally the vaporized target material will be deposited over the substrate. So this is a simple technique, but the parameters which control the quality of the coating are: first one is the purity of your target material, then your purity of the base material or substrate, then moreover the distance between the target material as well as substrate. So these all will affect the quality of the coating. And here also the coating won't be uniform. As your target material is vaporized, it can deposit anywhere. It is not essential that it has to it has to be deposited only on the substrate. It can be deposited anywhere. So that is a major drawback, and it lacks uniformity. The coating thickness won't be uniform. And coming to the application, this is mainly used for enhancing the wear resistance for cutting tool. Another important process is the surface hardening process. So here I am showing you the flame hardening as well as laser hardening. So if you look at the flame hardening, you will be having a base material to be hardened. So you are going to heat the surface of the material by means of oxyacetylene flame. And once you are heating by means of oxyacetylene flame, the surface of this region will be taken to the austenitic zone. And later on, if you are applying quenchant, so the austenite will be transformed to martensite, and as a result, your material gets hardened. So that is referred as a flame hardening. And if you look at the laser hardening, so we will be having a base material. So you are irradiating the surface of the material by means of a laser beam. So what will happen is intense heat will be applied over the substrate, and as a result of that, your material will be taken to the austenitic region, and here self solidification will take place, and as a result of that, austenite will be transformed into martensite. So here I want to say you that the solidification involved in this process is extremely high. It will be from 10 raised to 6 Kelvin to 10 raised to 8 Kelvin per second. And as a result of this, you will end up with a very good hardened surface. And the major difference between this flame hardening and laser hardening is, so flame hardening is a low energy input process. That is, you need to supply more amount of heat to take the surface of the material to the austenitic zone. So once you are heating for a prolonged period of time, what will happen is the grains present on its surface will tend to grow. Once the grain tries to grow, what will happen is your mechanical property will be affected. On the other hand, if you go for laser hardening, it comes under high energy density process. So wherein you need to apply only a very minimum amount of heat. So once you are applying minimum amount of heat, your grain growth will be restricted, and as a result, you could end up with a very substantial improvement in the wear and corrosion resistance. So this is the specialty of laser hardening when compared with your flame hardening. So this is one of the example wherein laser hardening was performed over a blade, undergo some plastic deformation, and moreover it will undergo deterioration. So in order to prevent that, you can apply laser hardening. You can also go for some sort of coating, but laser hardening is the cheapest technique. So that's why generally people will go for laser hardening rather than other coating technique. And this is the equipment wherein laser hardening was performed. And your laser hardening can also apply over the rails. So when a train is rolling over the surface of your rail, so there will be a friction between your wheel as well as rails. So as a result of this, your rail will be subjected to severe plastic deformation, and this will in turn lead to some amount of fatigue wear. So if you want to enhance the fatigue resistance or the fatigue life of this particular rail component, then it is better to go for laser hardening. So it has been reported that if you are undergoing laser hardening over the rail, you can reduce the friction coefficient by 25 to 40%, and you can also minimize or you can reduce the crack propagation rate by 60 to 80% when compared with the untreated rail. Another important technique is laser cladding. So here it is more or less similar to that of the laser hardening process, whichever I have discussed earlier. The only difference is apart from irradiating the surface of the material by means of laser, you are also injecting some powder. So here you can see that. So this is the material to be modified. So initially you are irradiating the surface of the material by means of a laser beam. So along the same axis, you are also feeding powder. So the powder particle will absorb the heat energy from the laser melt, and it gets completely melted, and finally it will be just coated over the surface of the material. So that is known as laser cladding. And here the most important thing is the parameters which control the quality of the cladded layer is, first one is the power input. So that depends upon the material to be modified. So another thing is the angle at which you are going to feed the powder, whether it is along the axis of the laser beam or you are feeding separately. So that parameter will also play a vital role in determining the quality of the cladded layer. And another important thing is the traverse speed. That is, while cladding, either your workpiece or your laser beam will be moving in certain direction. So that is known as traverse or scanning speed. That will also affect the quality of the cladded layer. So this is about cladding, and you can perform this laser cladding in the turbine blades also. And there is one more technique known as laser alloying. In the laser alloying, the principle is exactly similar to that of the laser cladding, and there are two differences between laser cladding and laser alloying. So the differences are, first one is, if you go for laser cladding, the thickness of the cladded layer will be more than 600 micron. You can maximum go up to 1000 micron. So whereas if you go for laser alloying, the thickness will be limited to a maximum of 20 micron. So that is the first difference. So another thing is, in the case of laser cladding, the dilution between your base material as well as the cladded layer will be very high. That will be more than 15%. So whereas if you go for laser alloying, the dilution between your base metal and the cladded and the powder, that is cladded layer, will be very much less. That is maybe less than 15%. So these are the differences between laser cladding and laser alloying. Now we are going to discuss about thermal spray coating. So if you want to develop a coating to have a very good wear resistance, and if you want to develop a very thick coating, then normally people will go for thermal spray coating. So this is how your equipment will look like. So coming to the principle of thermal spraying technique. So initially material in the form of rod, wire or powder is fed into the high temperature zone. So once the material is fed, what will happen is in the high temperature zone, your material gets melted, and finally the molten particles are accelerated toward the substrate, which is held at some distance. So once the molten particle impinges over the surface of the substrate, so solidification takes place. So during solidification, your molten particles will try to flatten, and finally it gets deposited. So if you are visualizing, or if you are visualizing the coated layer by means of a scanning electron microscope, you can see a lot of layer by layer deposition. And if you classify thermal spraying techniques, you can have more than 4 classifications. That is, first one is the plasma spraying technique. So this is the most important technique followed in almost all part of the country. And another one is the vacuum plasma spraying. Then detonation gun spraying. So this is otherwise known as a D-gun spraying technique. And next one is the high velocity oxy-fuel spraying technique. Now if we go for the plasma spray technique, so this is the schematic diagram for a plasma spraying technique. So this mainly consists of cathode and the anode. So tungsten will be acting as a cathode, and your copper will be acting as an anode. So whenever the primary gas, especially argon, is allowed to pass between the cathode and the anode, they get ionized and transformed into plasma. So you can see a blue colored region. So that is nothing but the plasma, ionized gas. So this plasma flame will have a very high temperature of around 10,000 to 20,000 Kelvin. So you can see a powder is being injected from the top. So the powder particle will absorb the heat energy from the plasma flame. So it gets melted, and finally the molten particles are accelerated towards the base material. So thereby you will be getting a deposition. So this is how your plasma spray technique works. And here what I want to say is the temperature induced in the plasma region will be extremely high. So that is the advantage of plasma spraying over some other techniques. Since the temperature is very high, what you can do is you can go for coating any sort of high melting point ceramic material. So that is the advantage of plasma spraying technique. And if you look at the parameters which control the quality of the coating, so the first parameter is that which you are going to, you will be supplying argon gas for producing plasma. That the flow rate of the argon gas, so that is also one of the most important parameters. And the distance between the tip of the nozzle and the substrate, so that is known as standoff distance. So these all plays a vital role in determining the quality of the coating. And now we are going to discuss about the most important concept, that is thermal barrier coating. So initially, while I was discussing about the applications, I'm just I have mentioned about the thermal barrier coating. So actually, in internal combustion engine, only 33% of the heat energy being effectively converted into work. So among which some amount of heat loss, maybe around 5 to 10% of the heat loss occur over the piston crown. So if you want to retain those heat it is going over the piston crown, then we want to go for coating some sort of hard ceramic coating. So there are lots of ceramics coatings available. Among all the ceramics coating, yttria stabilized zirconia, that is referred as YSZ. So this kind of coating is said to have the lowest thermal conductivity. If you are providing thermal barrier coating over the piston crown, you can retain more amount of heat, and as a result of that, your efficiency may increase from 33 to 38%. So that is why we are discussing about thermal barrier coating. So another research one can carry out is, so if you look at the IC engine, the piston will be reciprocating inside the cylinder liner. So due to that, lot of friction will be there, and either your piston ring or cylinder liner may undergo wear. So if you want to enhance the wear resistance, you can go for some sort of ceramic coatings either on the piston ring or cylinder liner. And thermal barrier coating can also be applied on turbine blades. So if you consider the gas turbine, so gas turbine material, so in general it is made up of nickel based superalloy. So that will be subjected to severe deformation, and moreover some material degradation, erosion may occur. So a lot of problems will be there. So in order to prevent this turbine blade from erosion and plastic deformation, again we want to go for thermal barrier coating. So now let us see the construction of thermal barrier coating. So in general, people will think that thermal barrier coating means directly you can take the base material and just you can apply yttria stabilized zirconia. So that is the wrong concept. So if you look at the construction of thermal barrier coating, so initially you will be having a base material. So that is nothing but nickel based superalloy. So this is the turbine blade material just now I discussed. And if you are directly coating yttria stabilized zirconia material over this particular nickel, what will happen is it won't adhere. So because the thermal expansion of yttria stabilized zirconia is entirely different when compared with your nickel. So as a result of this, you have to introduce a bond coat in between this yttria stabilized zirconia coating as well as nickel based superalloy. So you can see a blue colored region, that is the bond coat, which is being intentionally introduced between yttria stabilized zirconia and nickel. So this bond coat will make your yttria stabilized zirconia coating to get flue gas. So thereby it will form a layer. So that is nothing but alumina, Al2O3. So that alumina is referred as TGO, that is thermally grown oxide layer. So what I want to say is, in between the bond coat and yttria stabilized coating, you can see a very thin layer, so which is developed due to the interaction between the bond coat material as well as your hot fluid gas. Thereby, TGO is developed. So here, what will happen is, if you are entirely visualizing the thermal barrier coating, now you will have a nickel-based superalloy at the bottommost region, and over which you will be having a bond coat. So this is made up of nickel, chromium, aluminum, and its thickness will be ranging from around 100 to 600 micron. And subsequently, you can see a very thin layer, that is TGO, thermally grown oxide layer, and it will be having a thickness of around 2 to 10 micron. And above that, you will be having your main coating material, that is yttria stabilized zirconia, and its coating thickness may range from 100 to 600 micron. So what will happen is, in most of the papers, it has been reported that, especially in the thermal barrier coating, the failure happened exactly at the TGO layer. So because if the TGO thickness is exceeding 10 micron, then the coating exactly fails at the interface between the TGO as well as TBC. At the same time, if the TGO thickness is less than 2 micron, in that occasion also, the failure will exactly happen at your TGO layer. So what I suggest for all the researchers is, people can study or change the thickness of the TGO from 2 to 10 micron, and one can study the effect of TGO thickness on the engine performance. So that will be a very good research work. So many people are doing yttria stabilized zirconia coating, and they are studying the thermal efficiency of IC engine and everything, but nobody has focused of varying the thickness of TGO. And whoever wants to pursue research in thermal barrier coating, they got. So next one is the vacuum plasma spraying. So that is referred as VPS. So this vacuum plasma spraying is exactly similar to that of the plasma spraying technique. So I will show the plasma spraying technique once again. So if you look at the plasma spraying technique, what will happen is, so already I explained. So the molten particle which is coming from the plasma flame, so that will be directly undergoing interaction with the environment. So environment contains water vapor. So the hydrogen present in the water vapor will react with this molten particle. And as a result of this, when this molten particle solidifies, the hydrogen will be coming out, thereby leaving a lot of pores in the coating. So due to the presence of hydrogen, you finally will end up with a lot of porosity in the coating. So even if you are optimizing several parameters, you cannot reduce the porosity of this plasma spraying coating less than 5%. So what I want to say is, so in general, the plasma spray coating will have a porosity of maximum 20%. The porosity range will vary from 5 to 20%. So if there are a lot of very bad impact over the corrosion and wear resistance. So if you want to prevent this porosity, then you have to perform the entire plasma spraying inside the vacuum. So that is why we are going for vacuum plasma spraying. So you can see that the entire plasma spraying equipment is enclosed in a vacuum environment. So thereby, if you are measuring the porosity after performing coating, definitely your porosity will be reduced to maximum extent. So I can assure you that the porosity will be less than 5%. The next one is the high velocity oxyfuel process, and here you will be having a chamber. So inside the chamber, you are going to supply oxygen flame. So combustion will take place. So powder is being fed along the same axis. The powder particle will absorb the heat energy from the combustion flame, and finally it gets melted, and it will be allowed to accelerate at a very high velocity over the substrate. So here I want to emphasize that the velocity of the molten particle will be substantially higher when compared with the plasma spray process. So while discussing about the plasma spraying process, I was mentioning that the temperature will be maximum. that in the same process, the velocity was very minimum. So on the other hand, if you look at the velocity involved in this high velocity oxyfuel process, so your velocity will be around 1330 meter per second, which is substantially higher when compared with that other plasma spray velocity. So due to high velocity, what will happen is, so the interaction of this molten particle environment will be minimized, and as a result, you can end up with a very low porosity. So if you look at the porosity of the deposited coating, and if you are measuring that, definitely the porosity will be less than 2%. So that is the advantage of having high velocity. Another important advantage of high velocity is, since it is the molten particle is traveling at a very high velocity, you can end up with a very good adhesion. So these are the two advantages when compared with all the remaining APS, atmospheric plasma spraying process, and VPS process. And moreover, the major drawback here is the temperature generated in this particular HVOA process is very low. So there I was saying that temperature will be around 10,000 Kelvin. Here it will be less than 4,000 Kelvin. So due to very low temperature, you cannot deposit a very hard ceramic coating. For example, if you want to deposit a titanium borate, that is a ceramic, so its melting point will be very much higher. So in that occasion, you cannot go for preferring HVOF, because you cannot melt that material. So in that titanium borate coating, you can always prefer plasma spraying. And if you want to develop a coating for very good corrosion resistance, in that occasion, you need to have minimum amount of pores. So in that situation, you can go for high HVOF rather than plasma spraying. So based upon application, you are going to prefer what kind of technique you are going to adopt. So another thing is detonation gun spraying. So this process is more or less similar to that of the HVOF process. Here you will be having a barrel, so acetylene flame. So once you supply oxygen and acetylene flame, you are having a spark plug. You are going to inject the spark. So combustion takes place. So the combustible gases will produce detonated wave. So the detonated from the top, the powder particle will absorb the heat energy from the detonated wave, and they get melted, and this molten particle will be accelerated towards the substrate at a very high velocity. Maybe the velocity involved in this process will be slightly higher than that of the previous process. And as a result, and moreover, the porosity involved in this process is very less, because the velocity involved is very high. So the interaction of this molten particle with the environment will be highly restricted, and as a result, you can end up with a porosity even less than 1%. So that is the major advantage of detonation gun spraying technique when compared with all the other techniques. And another important thing is the difference between high velocity oxyfuel spraying and detonation gun spraying is, so in the case of HVOA process, we got a continuous coating. Here the coating will be not continuous. So for each and every spark injection, only certain percentage of material will be deposited. So I can say that here it is discontinuous. And if you compare the differences between plasma, degon, and HVO process, you can see that this is one of the case study while depositing nickel powder over the stainless steel substrate. And if you look at the plasma spraying, the velocity is very less. It is varying from 100 to 150 meter per second. So this is for nickel powder. And at the same time, if you look at the temperature, it is around 2700 to 3500 degrees centigrade. And the kinetic energy is 0.005. So if the same powder is deposited by means of some other process, you can compare. In the case of degon and HVO process, you can see maximum velocity 600 to 800 meter per second. So due to this, definitely the amount of porosity will be less. And at the same time, the temperature will be varying between 1500 to 2000 degrees centigrade. So this temperature kinetic energy. So first thing is you have to go for taking the cross section of the sample. So this is the schematic diagram of the cross sectional view of the coating. So here you can see a base material that is indicated in blue color, and over that you'll be having a coating. So if you go for analyzing the surface roughness of the base material, so in general you should always have higher surface roughness in the case of substrate, because if you have more roughness, there will be a very good mechanical interlocking, that is bonding will be very much nice. So on the other hand, if you look at the surface roughness of your coating, it should be minimum, because if you are having maximum surface roughness on the coating, so it will induce corrosion and wear. So that is why generally for base metal or substrate, you should have very high roughness, and whereas if you go for coating, you should always have very low roughness. And moreover, cohesive strength is not higher, otherwise your coating will undergo delamination. Another important thing is you can expect oxide inclusion. So especially if you go for plasma spraying, definitely some oxide inclusion will be there, because I told that the molten metal, when it is coming out from the plasma flame, it has the tendency to interact with the environment. So environment contains hydrogen and oxygen, so your oxygen can easily enter into that molten material, and finally it will be present as an inclusion in your material. So oxide inclusion will be there. So you have to alter the parameters in such a way that you should end up with a low oxide inclusion. So that is about your evaluation of coating quality. And this is the cross-sectional view of the coating, and this is the scanning electron microscopic view. And here you can see that the black colored region refers to the base material or substrate, so whereas the white region represents the coating. So as per this, one can say that no distinct interface was observed between the coating as well as the substrate. So this ensures very good adhesion, and that is why it is written as excellent adhesion. And moreover, if you are visualizing this particular image, number of pores observed was found to be very much less. And if you are using some software and if you are measuring the amount of pores present in this particular region, definitely the porosity will be less than 1%. Because I already told that in the detonation gun spray process, the velocity involved is very high, so that the interaction with the environment will be minimized. As a result, you will definitely end up with less than 1%. Definitely, you can expect very high micro hardness. So micro hardness will be carried out across the cross section of the coating using viscous hardness testing machine. And moreover, since the coating is very uniform and dense, you can expect a very low thermal degradation. And moreover, you couldn't see any oxide inclusion. And moreover, if you are having this kind of hard, dense and uniform coating, definitely you will have very good physical properties. Tribology is nothing but study of friction, lubrication and wear. And moreover, in this image you can say that the coating thickness is uniform throughout the entire material. If you measure the thickness, I can say that the thickness will be approximately 300 micron. At the bottom you are having a scale, it is mentioned as 100 micron, and if you are placing the scale over the coating, it will be almost 3 times. So it will be around 300 micron thickness. So this is the surface morphology of the plasma spread coating. So previously I found the cross-sectional view, and this is the surface morphology of the coating. And if you analyze the surface morphology, one can see a very good splats. So splats is nothing but a fully melted particle. So generally what will happen is, so whenever you are injecting the powder inside the plasma flame, the powder particle will absorb the heat of the day and it gets completely melted. So once this completely melted particle impinges over the base material, it will undergo solidification. So after solidification, your that is molten metal will be flattened. So thereby it will be forming a splat. That flattened region is referred as splats. You can see flattened molten particle. So this is referred as a splat. It is just resembling like a pancake-like structure. It will be, if you are visualizing, it will be exactly like a pancake. And this splat will have a very weak grain boundary. For example, if a crack is being initiated at this splat, what will happen is the crack will be propagating in a rapid manner, and finally it will lead to failure of the coating. And if you want to prevent that, what we have to create is, we have to end up with some amount of unmelted particle along with the splat. So if that is the case, the propagation cracks may be arrested. So in general, what I want to say is, whenever you are going for any thermal thermal spraying process, definitely you will end up with these kind of splats in the microstructure. And finally, we are coming to the last topic about the plasma spray nanoceramic coatings for biomedical applications. So normally HIP and NEJAN processes have been most widely performed in almost all parts of the world. And in 2030, it is expected that nearly 2.7 million people will be undergoing surgery in USA alone. And this may be due to aged populations, accidents or diseases. So if you look at the modulus comparison chart for bone with respect to various biomaterials, one can understand that. So initially 316L stainless steel have been most widely used as a biomaterial. And if so the modulus of this steel is substantially higher when compared with that other bones modulus. So if you look at the bottom, you can see that the bone is having a modulus of elasticity of around 20 to 30 GPa. So it is mentioned that as 30, generally it will be from 20 to 30. So due to the huge mismatch in the moduli of your stainless steel as well as the bone, what will happen is, so your implant will undergo loosening effect. So that is technically referred as stress shielding phenomena. So if you want to minimize this loosening or stress shielding phenomena, you need to select the appropriate material in such a way that it should have a modulus of elasticity somewhat close to that of the bone. So people thought of searching for some other group of alloy, and among all these material, this titanium 13 niobium 13 zirconium alloy is said to have the modulus somewhat close to that of the bone. It is having a modulus of around 77 GPa, which is slightly more than that of the bone's modulus. So even though some other materials are having the modulus very close to that of the bone, the reason for not choosing that kind of material is the presence of tantalum. If tantalum is more, means it is expensive. That is why people didn't use some other alloy, even though its modulus is very less. So in our research work, we have preferred titanium 13 niobium 13 zirconium alloy because the modulus is somewhat close to that of the bone, and moreover, the presence of niobium and zirconium will enhance the corrosion resistance of this particular material. And this is the schematic picture of the hip joint. So you'll be having a femoral stem at the bottom. So this is being made up of either titanium or stainless steel, and you'll be having a femoral head which is made up of cobalt, chromium, molybdenum alloy. And since the femoral head as well as the femoral stem are made up of two different materials, so what will happen is there will be a small fretting wear between two mating parts. So one can propose the entire femoral head as well as femoral stem to be made up of titanium or stainless steel alloy. And moreover, if you look at the topmost region, that is known as acetabular cup. So that is being made up of ultra high molecular weight polyethylene. So whenever the body is in movement, what will happen is there will be a friction between the femoral head as well as acetabular cup. So this will in turn leads to more amount of friction, and finally wear will take place. So if you want to enhance the wear resistance, we want to go for some sort of nanoceramic coating over the femoral head. So thereby you can prevent the loosening of implant, etc. Hence, we went for nanoceramic coating. So the major reason for preferring nanoceramic coating is, first one, if you adopt nanoceramic coating, you will have maximum wear resistance and the bond strength will be extremely high. And moreover, you will have maximum crack propagation resistance, and it will have excellent hardness and less porosity. And these all are mainly due to the so osseous integration is nothing but integration of bone with the implant. So we have performed 3 different types of coating. So as I said, we have preferred titanium 13 niobium 13 zirconium alloy as a substrate, that is base metal. And in the first case, we have deposited alumina 13% of TiO2 coating. And in the second case, we have preferred the same titanium 13 niobium 13 as a base metal. And above that, we have used yttria stabilized zirconia coating. And in the third case, we preferred zirconia as the first layer, and subsequently we have deposited alumina titania coating. So the reason why we have preferred this alumina titania coating is, so it has been reported that this alumina 13% of TiO2 coating has been substantially used in naval application, as it is having very good corrosion and wear resistance. And moreover, this alumina and TiO2 is said to be biocompatible. So that is the reason why we have chosen this. And moreover, zirconia is being oftenly used as a ceramic cup. So that all these three materials for coating. So this is a morphology of a starting powder. If you look at the nanostructured aluminum titania powder, so these powders were procured from United States. And if you look at the particle size of this nanostructured aluminum titania coating, the particle size range from 30 to 130 micron, and the shape was found to be highly spherical in nature. And whereas if we go for nanostructured zirconia, so it had a particle size of around 70 micron, almost 50 to 70 micron, and the shape was found to be angular. And this is a surface morphology of the plasma spread coating. So I told you that we have deposited three different materials for coating. So first case, this is the scanning electron microscopic image of nanostructure, a combination of fully melted particles. So that is known as splats. So I already discussed about the splat formation, and moreover, you could see some amount of unmelted particles. So the reason for the formation of these fully melted particles and unmelted is, so whenever the powder particle is fertile, whatever powders which are passing exactly towards the axis of the plasma flame, they get completely melted, and thereby once it impinges over the surface of your base material, it will undergo solidification, it will flatten, and thereby you will get a fully melted splats. This I have already explained. And the particles or the powder particle which are moving away from the axis of the plasma flame, that remains unmelted. So that unmelted particles will be just embedded inside the fully melted splats. So that is why you could see some unmelted particle. It is represented here. It is being interlocked or embedded in the fully melted splats. So if you are having a microstructure with a combination of fully melted particles and unmelted particle, so that is referred as bimodal microstructure. So here the major advantage of having bimodal microstructure is, so as I said to you earlier, that the splat will be having a very weak grain boundaries. So for example, if a crack is being initiated in this particular splat location, what will happen is the crack will easily propagate, and the propagation of crack will be completely arrested by the presence of hard unmelted particle present in the microstructure. So that is the advantage of having bimodal microstructure. So this is about nanostructured aluminum titania coating. And if you go for the surface morphology of zirconia coating, you could see a lot of pores and cracks. So whereas if you go for bilayered coating, so you can see a very dense and compact microstructure, and moreover you could see a lot of fully melted splats with very few unmelted particles. So the reason behind the formation of this fully melted particle is, so initially you have deposited zirconia coating, first layer. So this zirconia is said to have the lowest thermal barrier coating. So this I already explained when I was talking about thermal barrier coating. So the first layer is having a very low thermal conductivity. So as a result of this, this heat have been effectively utilized by the subsequent aluminum titania coating. So thereby you have ended up with a completely melted region. So that is why you could see a lot of fully melted splats, and only a few unmelted particles were noticed here and there. And moreover, if you are visualizing the amount of pores, it will be very less when compared with, and the coatings were cut across its cross section, and these are the scanning electron microscopic view across the cross section of the coatings. So if you go for the zirconia coating, you can see that is white colored region represents the coating, and that black region is nothing but your base material or substrate. So while coming to zirconia coating, you can see a very distinct interface between your coating as well as base material. So this indicates that it is having very poor adhesion. So on the other hand, if you go for aluminum titanium coating, the interface between the coating and the base material was not noticed. So this ensures a good adhesion. So similarly, if you go for the bottom figure, that is in the case of bilayered coating also, there is no distinct interface between the coating as well as the base material. So this ensures a very good adhesion. And moreover, if you measure the thickness of all the three coatings, it was found to be approximately 100 micron. And micro hardness measurements were carried out across the cross section of the sample by applying a load of around 100 grams. And based on the result, you can very well see that the bilayered coating possesses maximum hardness when compared with all the other coatings. So this is mainly due to the presence of very dense and uniform microstructure observed in the SEM image. And moreover, the yttria stabilized zirconia coating has got very low hardness. And this is mainly due to the presence of pores and cracks observed in the coating. So we did some corrosion testing. So corrosion testing was performed using the equipment known as potentiostat. So this is the potentiostat. So at the bottom right hand side, you can see a small beaker. So here you will be having a provision for holding 3 electrodes. One is the standard electrode, and another one is the reference electrode, and the third electrode is the workpiece. So that is the coated workpiece will be held in this particular location, and this is being exposed to the solution taken in a beaker. And here the principle is we will be applying potential and we will measure density. So we will be testing it for corrosion for almost 5.5 hours. So after corrosion testing, so you will be getting this kind of curve. So based on this curve, one can say that the corrosion density the current density is going on increasing with increasing potential for all the 3 coatings. However, if you look at the table, in the case of table, in the case of bilayered coating, the corrosion resistance was found to be very much minimum. That is the current density, which is represented as ICAR. So this value is very high corrosion resistance, and this is attributed to the presence of very dense microstructure. So I have already shown the microstructure there. You couldn't see any pores. So that has resulted in a very good corrosion resistance for bilayered coating. So on the other hand, if you look at the zirconia coating, so it is indicated by the green color graph. So it's a current density, that is ICAR value will be very much higher when compared with the bilayered coating. And once the corrosion current density is very high, it indicates that it is having very poor corrosion resistance. So this is mainly due to the presence of more pores and cracks observed in the microstructure. So while showing the image, I have shown that lot of cracks and pores were there. So that cracks and pores present in that particular coating has paved the way for the solution to attack the base material. That is why the zirconia is having very poor poor corrosion resistance when compared with the above bilayered coating. And testing was performed using a reciprocating wear testing machine. So this is the equipment. Actually, we will be having a provision for holding the sample. It will be a rectangular sample, which will be having a dimension of around 25 into 20 into 4 mm, and you will be having a provision for holding the ball. So we have preferred alumina as a counterface material, alumina ball, and this alumina ball is allowed to slide over the surface of the sample. And this testing was carried out for almost 13.5 hours. That is 1 lakh cycle we have tested. And at the end of testing, we have taken the one surface morphologies. And if you go for the first coating, that is in the case of bilayered coating, so one can say that after 1 lakh cycle of wear testing, more amount of particles are being retained. And this indicates that this particular bilayered coating is offering very good resistance to wear. In addition to that, you can also see a white particle is sticking over the surface. So this mainly happens because, so if you look at the hardness of the bilayered coating, it was around 1074. Since it is having maximum hardness, during wear testing, material transfer has taken place from the counterface material, that is from the alumina ball towards this material. So that is why you could see a hard particle sticking over there. And if you are analyzing using IDAX, it will confirm the presence of alumina. So it actually came from the alumina ball. And if you look at the one surface morphology of your alumina titanium coating, so here also you can see lot of particles are retained after 1 lakh cycle of wear testing. And this is mainly due to the bimodal microstructure. So I just told about the advantages of bimodal microstructure. So due to the presence of bimodal microstructure, during wear testing, you are unable to remove more materials. So that is why cycle of wear testing. And moreover, at the bottom you can see the one surface morphology of the zirconia coating. And here you can see nothing is left out after 1 lakh cycle of wear testing. And this is mainly due to the presence of pores and cracks. So while discussing about the same image, we have seen a lot of cracks and pores. And during wear testing, this has completely damaged, and it has undergone ploughing effect, so that you couldn't see any debris, wear debris, even after 1 lakh cycle of wear testing. And finally, we have carried out some scratch test. So in order to ensure adhesion, so scratch testing machine will be resembling just like your wear testing machine, and the only difference is in the scratch testing machine we will be having a diamond ball, and the diamond ball is abraded over the surface of the coating material. So after scratch testing, we will go for analyzing the image using scanning electron microscope, and you can see these kind of images. In the case of nanostructured zirconia coating, you can see the depth and width of the crack was found to be, the depth and width of the scratch track was found to be very much higher. So this indicates that more amount of material removal has taken place. So because the reason is, since it had a very large number of cracks, so the material removal was found to be very much higher. So this indicates that this particular coating is having very poor resistance to scratch. And if you look at the nanostructured alumina titania coating, the depth and width of the crack was found to be very much meager, and this is mainly due to the bimodal microstructure. And moreover, if you look at the scratch track of bilayered coating, so the width and depth of your scratch track was extremely low, and this is mainly due to the compact and dense arrangement of grains in the microstructure. And based on this, one can say that this bilayered coating has excellent resistance to scratch. To summarize this case study, I can say that this bilayered coating possesses dense and uniform microstructure, and very less porosity was observed. And based on hardness, you can see a substantial improvement in the hardness of bilayered. And finally, to conclude, HO and all the organizers. Hello.
Hi, sir. So it was a very good presentation. Thank you, sir.
Hello. Hello, sir.
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 It was a very good presentation. Is it audible? Excuse me, sir. Is it audible?
Yes, sir.
Thank you, sir. Thank you, sir. Sir, you can proceed, sir. Yes, sir.
Sir, few of them have asked the questions, sir. I will read
Yes,
it
sir.
out. I can. Okay.
Yes, sir. Yes, sir.
Which type of coating material can be used for aluminum composite to obtain good bonding?
So if you want to end up with a very good bonding for composites, what you can do is you can go for laser remelting, sir. Actually, in the case of composites, you'll be having reinforcement. So once you are undergoing remelting, definitely this reinforcement will reorient, and you can a very good bonding between the reinforcement and in the sense the bonding between your reinforcement as well as matrix.
Okay. Thank you, sir. Now I invite. Thank you, sir.
Thank you, sir.
Now I invite Mr. Pradesh to deliver the vote of thanks.
Thank you. On behalf of the Narayana College of Engineering, and all the participants of the webinar, we have to thank the resource person, Dr. Sathish, for sharing your valuable knowledge in surface engineering with us. It will definitely create innovations in the minds of every participant. We thank all the participants for our active participation and to make this webinar a great success. Thank you, one and all. Regarding e-certificate generation, we request all the participants to submit the feedback form, which is given in the description of the YouTube and also in the Google Meet chat box. Thank you.
Okay, thank you, sir.
Thank you. Thank you.
Shall I leave, sir?
Yes, sir.
Okay, thank you very much, sir. Thank you.
Thank you.